since gravity is space-time, maybe it's not quantum. It's different than the other forces, and is intrinsically classical. Well, if you do this experiment, if you come out right, what we expect, this is ruled out as well. So that's the situation. There are many tentative theories, but many of them are in tension with recent empirical data. Many are extremely incomplete, and some are disappointing also in what you hoped to do with this theory and didn't work. So let me now, after this panoramic of experiments and theories, zoom to loop quantum gravity, which is, in my opinion, the best candidate, not the only one, but the best candidate we have for a theory of quantum gravity. What I'm going to do is to tell you roughly what it is, flash a slide with all the equations. So you see all the equations, this once. And then talk about what one does with that, what it tells about space and time. So first of all, since I mentioned that, there's no violation of Lorentz invariance, the theory is Lorentz invariant, so it's okay with that part of experiment. There are no extra dimension, no supersymmetry, okay with that part of what nature says, and no violation of quantum mechanics. So quantum mechanics is just quantum mechanics. And the strength of the theory, in my opinion, is that it's conservative in some sense, very conservative. Namely, the physical hypothesis is just generativity and quantum mechanics. So the idea here is there a quantum theory? Can I write a quantum theory whose classical limit is generativity? It's almost a well-posed problem, right? Mathematically. Can I write a Hilbert space set of operators and transition amplitude such that in the classical limit, I get the theory of gravity that works so well, general relativity, with black holes and gravitational waves and so on. And you probably know that the difficulty is that if you do that in the usual way in which we do quantum electromagnetism, or QED, or quantum strong interaction, it doesn't work because there are infinities that cannot be treated. You know that in quantum electromagnetism there are infinities, but there's a way of treating them and dealing with them, which is called normalization theory. It does not work in general relativity. And what happens is, and I'll explain why, what happens in loop quantum gravity, the theory is non-perturbative. So it's not a perturbation expansion around space-time. And space-time itself is treated quantum mechanically non-perturbative. I just told you from the experiment that space-time can be the superposition of space-time. So you don't assume that there is a given space-time, and therefore you don't assume that there is infinitely small distance. And the theory itself shows that there is no infinitely small distance. Why? Well, because quantum mechanics shows you that there are gaps, there is discreteness, right? Think of the harmonic oscillator energy. You can have one energy, and that's it. There is no half the minimal energy of the harmonic oscillator. There's no state with 1/5 of h bar omega. Okay, so there's discreteness down there, and because of this discreteness, quantum discreteness, the geometry of space-time, gravity, is discrete, and because of that, there's no infinity small, and because of that, there's no infinities. Okay, historically, just to say you why loop. Historically, the theory emerged because back in the 60s, I suppose most of you were not born, Bryce DeWitt and John Wheeler wrote sort of the quantum equation for quantum gravity. It's a Schrödinger equation for general relativity. There's a wave function where Q is a geometry, so it's not a variable, it's a field. And if you do a naive intuitive quantization, you get to this equation, which is badly defined. You can do anything, you cannot do anything. People work for that, but didn't go much far until in the late 80s, solutions of these equations were found, which were connected to loops. Loops here is gamma is a loop, is a closed line in space. And you can write the gravitational field, for those of you who know this mathematics, in terms of a connection, like the Maxwell potential, and the line enemy, the integral of the connection along the loop, or the holonomy of the connection along the loop, turns out to be a solution of this equation. So these strange loop states sparked a long work for sort of unraveling this equation, and quantum gravity was born, loop quantum gravity was born. And now, which is 20, 30 years later, this is loop quantum gravity in one slide. I promise you loop quantum gravity is a slide, this is it. I'm not going to illustrate these equations in any details. In fact, I'm just saying a couple of words about that. It requires a little course in mathematics, not particularly long. There's some group theory. It's something you can learn in a couple of weeks, or not even. But it requires some steps, and of course we don't have time to go that. What I want to tell you is the structure of these things. There's a Hilbert space, because all quantum gravity is a Hilbert space. The states are in a Hilbert space. So there's a well precise definition of Hilbert space. And what is strange is that the basis of this Hilbert space, the state of the quantum gravitational field, can be labeled by what's called spin networks. Spin network is it's a mathematical thing that Roger Penrose in the UK invented long ago, back in the 60s. In the back of his mind was a quantum description of space-time. It was just pulled from there, this mathematics. So it's a combinatorial thing. I'll come back to that. And on the Hilbert space of, with this basis, there are a set of operators, which certain commutation relation, certain algebra, and then you have transition amplitudes. Okay, so those of you who know a little bit of, quantum mechanics of a particle, you have Hilbert space, the operators, and the Hamiltonian that give you transition amplitude. In QED, you have the Hilbert space, the Fock space, the operators are creation, annihilation, and then you have the Feynman graphs to give you the transition amplitudes. And the transition amplitudes are between one of these states and another one, from a spin network to another spin network. And like in Feynman theory, Feynman graphs, you have sort of Feynman graphs that go from one spin network to another. But if you think that the dots here are the particles, this is a dot, a node of the spin network. This is a Feynman graph vertex, but there are also these links, and these links span sort of surfaces. So you construct this thing is called spin foam. Foam, because if you think of a foam, there are little surfaces that join in edges that join in vertices. And so you label the terms of these integrals. These are integrals of SU2, SL2C groups. One can prove that this is a finite. Everything is finite here, and you compute transition amplitude with these things. All right. So this is math. What does it mean? I mean, how is this connected to quantum gravity? Well, first of all, the way to think about these spin network states is that the nodes represent actual little quanta of space. Like the photons are the quanta of light. These are the quanta of the gravitational field, and since the gravitational field is space, this is a quanta of space. So little chunks of space, okay? And then in the theory, you can compute the geometrical aspect of this pieces of space, because the links tell you who is next to whom. So you can think like the polyhedra. They're not polyhedra because they're a quantum thing. And you can compute for each one of these the volume or the area of the faces that separate one from the other. And there's a standard calculation in quantum mechanics. You have an operator, you compute the spectrum of the operator. Then when you diagonalize the Hamiltonian of the energy, the energy of the atom or an harmonic oscillator, you get a spectrum. So you get a spectrum of the possible value of the area, for instance, or the possible value of the volume. Of what? Of anything. Just anything in space is made. The space is made by these junks, and the volume and the area are quantized in a with discrete eigenvalues. So you see, it's not possible to have arbitrary small things. There are no small things, no arbitrary small things. Like the spin of a rotating particle. Study quantum mechanics, you find out that it cannot be less than h bar half. That's minimum. There's nothing is rotating slower than that. Same here. There's no space smaller than that. So this spin network, this is a basis, right? General space-time can be a superposition of these things, but it's a basis. General space-time is a superposition of things, each one of which has a discrete geometry. And this last sentence here It's a key one. These are quantum states, but so they resemble the Fock space of QED, I mean photons. But there's a fundamental difference here. The photons, each photon live in space-time, move in space, is somewhere. These are not somewhere, because these are space themselves. These are the where. The space is made up granularly by these things here. And then you make transitions between a spin network to another spin network, so to a space, three-dimensional space to another three-dimensional space, and you describe a process, a part of space-time, through these equations that I told you that give you transition amplitude, the probability of going from this geometry of space-time to this geometry of space-time. And the way to think about that is that, you see, in quantum mechanics, you always have an observer or an apparatus, something that measures. And so you always describe a quantum process as seen from another system. And it's called Heisenberg cat, C-U-T, not C-A-T, Schrödinger cat. The Heisenberg cat is a separation between the quantum system and the observer, which of course you can move around. It's not, your prediction depends on where you put the Heisenberg cat, but if you move out, the final prediction is the same. And in quantum gravity, the system that you're observing is a region of space-time. And the Heisenberg cat is a boundary of this region of space-time. So imagine that in this region, I don't know, there's a black hole collapsing and going through a quantum process, evaporating, and then going through a quantum gravity transition, exploding. You think of this enclosed in a space-time region, so region space for a certain interval of time, and you compute the probability of something beginning and something after. Quantum theory tells us that many variables have discrete spectra. Discreteness is the core of quantum theory. That's why we call quantum theory. Quantum because a little quanta. And general relativity tells us that geometry is the gravitational field. So geometry is a physical variable. And since it's a physical variable, it's quantum. And since it's quantum, it's discrete. So when you put them together, quantum gravity tells us that geometry is discrete. And since geometry is discrete, the infinities of quantum theory are fake, are the result of the approximation where you neglect the discreteness of space. So you see, quantum mechanics and general relativity together save themselves from the disaster of quantum field theory. I'm going to give you a couple of applications of this theory, how it's used, what people are doing with these theories. Just one or two slides, no more, just to tell you how people are trying to get empirical support for this theory. One, of course, is cosmology, because early cosmology, the universe near the Big Bang, was definitely in a quantum gravitational situation. So you take this theory, try to apply what happened at the Big Bang. So it's, approximation work, it's a lot of papers, a lot of things, a lot of theoretical work. The bottom line, it's the core of the bottom line, because then there's much more to do. It's pretty simple. An expanding universe, this is a picture of an expanding universe, is described, the scale A evolved with time, grows according to an equation in classical general relativity, which is the Friedmann equation. So the books is this one. So the time derivative of A over A squared is proposed to some constant, and the density of matter. Now, if you start from full quantum gravity, you do approximation, blah, 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 you don't get to this equation, but you get to a correction of this equation. The correction is this extra term here, where rho is again the density, the energy density of matter, and rho PL is rho Planck, is a Planckian density. So it's a constant. And you see, when rho approaches rho Planck, so when you go back in time, and the density goes, the universe is smaller, so the density goes up, up, up. At some point, to get to the Planck value. 1 minus 1 is 0, so this becomes 0, and the velocity A at the expansion, when you go back in time, decreases. At some point, becomes 0. And in fact, you can continue the evolution. This can be done. It's just a sketch of the calculation, but you can be done doing the actual quantum evolution of the state, and you discover that it goes to 0. And instead, if you go back in time, instead of falling into a singularity or emerging from a singularity, there is a bounce. You come back. okay? Because there's a minimum, if you want, there's a minimum dimension. You cannot squeeze things too much. I mean, there is no zero dimension in nature. So at some point you bounce.